This is the solution video for question 4 for the modules of small circle of 2D stress and strain transformation. In this question, we have a strain rosette mounted on a beam at a 60-degree angle, and we have the following readings. We need to determine the in-plane principal strains and the maximum in-plane shear strain and average normal strain. In each case, show the deformed element due to these strains. So first of all, if anyone was in my tutorial, I try to treat this as a free body diagram. We cannot treat it as a free body diagram. These are sensors that read the strain in the element, and we actually have a formula which we use in order to solve questions or real-life experiments using that. So I've just pasted them in here. Feel free to pause the video to copy them down. So in our case, when we look at our element A, and B and C for that matter, I'm just going to draw here on the question. We actually want to obtain this angle here for A. And for B, we also want to obtain this angle to the positive, let's call it x-axis. And similar for our C as such. Right, so angle for A to the x-axis it's just 90 minus the 30 that's given in the question, which is 60 degrees clockwise. And same our theta B, we have the 90 degrees plus 30 in this case, 90 plus 30. 120. And for theta C, 180, right? Again, clockwise, all of them. And rather than me inputting these values that we have been given, in these angles that we just found, into this formula right here, I'm just going to include the written out solution for it. So again, go ahead, pause the video in order to see which values that you need in order to solve for this. What you'll find, again, they've just noted out where we got our angles. They input the values that we've been given for A. So here. We have 3 unknowns, but in our equation number 3 down here, because the angle is 180, we actually end up being able to solve for our normal strain in the x direction. And what we do, we input this value back into equation 2 and 1. And we do simultaneous equations about those ones. And we're able to find our normal strain in Y and normal strain, our shear strain as well. But what we're more interested in is from these values, we want to now construct more circle. And if you recall from our stress calculation, we had this CR squared method, and we can actually use it in here as well, because what we'll find is that most of our calculation is going to be exactly the same. So step 1, we want to find the center point. And our center point is, again, it's just the average, but in this case, it's the average strain. And we have these values as 250 plus minus 250. And yes, these are times 10 to the negative 6 divided by 2. Well, we'll find this is going to end up being 0. And then we want to do our step 2, which is our reference point. Again, our reference point, normal strain X, and shear strain. Shear strain. But unlike the stress calculation, when we talk about strain, our shear strain is always divided by 2. So our reference point A is located at 250 and half of our shear strain, which we got up here. So half of that is just 375.28. 6. So I'm just going to put that directly in here. Makes it easier for future calculations. Put that to the power of 6 outside. Step 3. Our last R refers to the radius. Again, our radius is simply just the square root out of our normal strain X minus our average strain squared plus our shear strain squared. Then 250 minus 0 squared plus, almost forgot, remember how I just said our normal strain, our shear strain, so it's divided by 2. So in here we'll have our 375 again, 128 squared. Quite easy to forget and get it confused with our stress, but that's basically the only difference. So 450.92 times 10 to the negative 6. Now that we have all these values, we can go ahead and construct our Moore circle. I'm just going to start by drawing the actual circle. The good part about knowing that our center point is at 0 is that our strain normal axis and our shear strain is just going to intersect at the center of the circle. So our horizontal axis and our vertical axis, move that to the center. And again, in the middle here, I have my center point. And my minimum principal shear strain, again, located on the left-hand side, and my maximum principal shear strain on the right-hand side. Then I also have my reference point A, and recall both the values were positive, so we're going to be in this quadrant right here. So I have my A. So A at 250 and 375.28. Then what we want to do, we want to go ahead and find our transformed element, which is going to be from our reference point to our principal plane, or the normal plane. So from reference towards our principal. And this is our 2 theta P1. And how do we find this angle? Well, it's quite simple from geometry. So from reference point A, all the way to the horizontal axis, what we'd find is that this is just our shear strain divided by 2, which is just our 375.28, right? And because our center point is located at 0.00, this dimension is obviously a lot easier to find than in some of the previous examples that we had, because this distance is simply just the same as our 250, which again is the same as our average. And in this case, only when it's located like that, it's the same as our normal strain in the x direction. So now that we have those values from geometry, we can go ahead and find our angle 2 theta P1. We know that tan 2 theta P1 is the shear strain divided by 2 on our average normal strain. So if we rewrite this, 2 theta P1 is the same as 10 negative 1 375.28 on 250. So 2 theta P1 is 56.3297 degrees, which is approximately 28.2 degrees in the element. So we just divide that by 2. And if we look at the direction which element A needs to turn in order to come towards the principal strain, so the transformed element, it's counterclockwise. I'm just going to note out here on our reference point A. So again, in here, this is our x, where our theta in the element equals to 0, but our theta rotates towards our principal stress, which is now going to be along our x dash, so the transformed axis, right? And lastly, before we draw out our element, the principal strain, pretty neat and only indication where we have the center point at 0.00, so at 0 shear and 0 normal strain. Minimum strain is simply just or minimum principal strain is simply just the negative radius. This is just this distance here, right? And for our maximum, again, it's just going to be our positive radius. So principal strain 1, or our maximum strain, is positive radius, which is 450. times 0.92 times 10 to the power 6. Minimum strain, negative radius, negative 450.92 times 10 to the negative 6. Last thing we want to do for this part is to draw the transformed strain. And I'm just going to do a small diagram down here. Original y and x, pretty standard. Our new or our transformed x and y, just realized I wrote y down here instead of x. So it's rotated counterclockwise, right? So it means our x is rotated this way at an angle of 28.2 degrees. So when we're talking about the angle, we're talking about this angle here. So that angle. Our y-plane is always, 90 degrees from the x. So transformed y-plane, transformed x-plane. Our original piece would have looked, or element would have looked something like this. Whilst the transformed element would change in the object shape, which means this part here is our stress 2 transformed and our principal stress 1. Sorry, this one is supposed to be y. Okay. We do have one more step, which is to draw out the shear strain transformation as well. And let's just note out where our maximum shear strain in plane shear strain is. So again, down here, similar to our shear stress, but just recall our maximum in plane shear strain is divided by 2. Which means that when we want to find our max we can't just say that it's the radius, but it's actually radius times 2, which gives us 450.92 times 2 times 10 to the negative 6, which is 901.84 times 10 to the negative 6. But we also need to know the transformation angle, and we start at the reference point A and we go towards the maximum shear strain axis. So in this case, the vertical axis here. And in terms of the location, it's counterclockwise. So if we go from A to our max in plane shear strain, it's clockwise. And this is, perhaps I shouldn't write that in there, but this is 2 theta S1. So how do we find that? Well, again, we can do that using geometry of this triangle, or we can just use our critical thinking and say, hey, well, it's 90 degrees between the shear plane and the principal plane here. So we can find that our 2 theta S1 is just our 90 degrees minus our 2 theta P1. So 90 minus 56.3297, which will be close to 33.7 degrees. And if we want to look into the element transformation, we just need the theta S1, which is divided by 2, so 16.8 degrees. And again, it's going clockwise. So when we draw the transformed element, again, this is our y and our x. This time around, though, our x has been transformed in the clockwise direction, which is this direction. So we have our transformed x plane going this way. Theta S1, 16.8. Again, it's not drawn to scale. 90 degrees from there, we have our transformed y. This time around, the object will look slightly different because our shear strain causes the kind of like the angle inside here to change, right? So a positive shear strain causes this angle to be smaller. So at the moment it's 90, but if it's negative, it will cause the angle to become wider. Just keep that in mind. So it will look something, again, fairly kind of estimated drawing. That dotted line will be our transformed element due to the shear strain. And in here, so in there, that distance between there and there, on both sides is our max in-plane shear strain divided by 2. And that is the end of this question.